You just heard a digital delay effect for guitar running on this custom hardware programmed in C for this STM32 microcontroller. In this video, we'll explore the basics of digital delay effects, how to implement them, what to watch out for, what parameters we can change, and how we can change the structure to alter the sound of this delay effect. As you'll see, the actual implementation of the delay effect is very simple, and all we essentially need is some feedback and some delay lines, but we'll go through in detail in this video. A huge thank you to PCBWay for sponsoring this video. I had these digital signal processing PCBs manufactured and assembled by PCBWay in China, and they did an absolutely fantastic job. For this, I used their PCB prototype as well as their PCB assembly service, but I oftentimes also use their advanced PCB service where they can do through-hole or HDI boards up to 60 layers and many different custom options. So I'd highly suggest you check them out. Links to them will be in the description box below. Make sure also to follow PCBWay on Instagram, as you'll see all of the cool designs they're producing and manufacturing, and sometimes you'll see my designs pop up there as well. There are a vast number of digital delay effects available to buy commercially on the market today. This could be for guitar, for other instrument types, for vocals and so on as plugins, but they all essentially have very similar underlying structures. For example, take here the TC electronic flashback delay on the left-hand side, and someone did a teardown on Reddit and showed the internal guts. And this kind of structure, at least for the hardware side, is very similar to what you'll see across many different effect platforms. You effectively have analog inputs and outputs in the form of these 1/4-inch jacks here that will feed through some analog front end for some filtering, amplification or attenuation, feed into a codec, which are ADCs and DACs in one single package, and then feed into some digital signal processing platform. For example, this Shark processor here. This might have some additional external memory, which we'll see why this might be needed for this flashback delay in this case, some power sections and so on. So for digital effects, oftentimes the hardware structure is very similar. You might have different memory types, different processing types, different analog front ends, but the building blocks are pretty much usually the same. The nice thing then is with this underlying platform, we can write all of our effects in software, and exactly what we're going to be doing today in this video. For this video today, we will be implementing a digital delay, specifically for guitar, but of course you could apply this to vocals or any other instruments as well. The reason I'm showing the flashback by TC Electronic is because this is one of my favorite delays, and it's also rather simple to understand, and we'll see the similarities between the delay we are implementing in this video and the effects and parameters we have on the TC Electronic. For example, we have an effects level, which sets the overall output level of the effect. We have a delay level, which sets the length of the delay or the time between the repeats of this delay. We have a feedback setting, which controls how many repeats we get and how they decay. And then we also have this selector switch on the bottom right, which selects between different types of delays. For example, the 2290 is a purely digital delay. Then we have an analog, which is maybe using some high-pass filtering, some modulation effects, and so on. And as we'll see, by varying the structure of the delay later on, we can achieve similar effects as the TC Electronic. The TC Electronic flashback also has, for example, different settings for quarter note, dotted eighth, and so on, and of course also tap tempo and bypass. That all being said, this might look a bit complicated to start with, but you'll see the underlying structure is actually quite simple. Keeping the hardware structure in mind, we have exactly the same hardware structure pretty much on our custom piece of hardware that we will be using in this video. Rather than a Shark DSP, we'll be using an STM32 microcontroller, which is pretty powerful. It contains enough processing power and also memory to implement digital delays on this in C as well. We have an ADC and DAC in one IC, this codec on the bottom, an analog front end, various power sections and so on, and we've seen this board in a number of videos. This is, however, just a mono pedal, so we just have a single input and a single output, but keep in mind, but digital delay is very easy to then implement also just stereo. Essentially, we just take a copy of the code and repeat that for a second channel. But this is the basic underlying hardware we will be using to implement our digital delay. At the heart of the digital delay is the delay line, and we've covered this before in a previous video called comb filters and delay lines. I'll leave a link to this video, of course, in the description box below, but this is video number 124 on my channel, where we go over the basics of comb filters and FIR comb filters specifically, as well as delay lines. That goes into a bit more of the theory and the maths behind comb filters and delay lines, so make sure to check that out if you're interested before you continue with this video. In essence, once we've sampled the signal from our ADCs, we are in discrete time. So we're working with sampled signals with, for example, floating point values per sample. That means we have a sample rate or sampling rate fs in hertz, and that typically might be for audio 44.1 kilohertz, 48 kilohertz, or even higher. The reason we want a delay line is that, as the name implies for our digital delay, we want to take an input signal and delay it by a certain amount. And of course, we'll do some other processing around that. But essentially, the delay line simply takes an input, x sub n, so x at sample n, passes it through this delay line block, and the output is simply a delayed identical version of the input. So if our delay line is set to have a delay of time 1 second, if we pass an input at t equals 0, we will get an output of the delay line at t equals 1 second. So effectively, the output is delayed by a number of samples. And for a delay line, we will typically denote the delay by k, and that's a number of samples. If we want to convert to the equivalent time delay, so td, we simply have to say k equals td times the sampling rate. So if we have a sampling rate of 48 kilohertz, 48,000 samples per second, we want a 1 second delay, 1 second times 48,000, and we get k equals 48,000. K can be an integer or a fraction. We'll be just working with integer delay lines in this video because it's a bit simpler, and the delay line itself is implemented using a circular or a ring buffer. We will be seeing it in this video as well, how to implement that, but make sure to check out the previous video, number 124, on comb filters and delay lines for a bit more depth. But the delay line itself is actually very, very simple, simply delaying samples by a given amount. That delay line then forms effectively the heart of our digital delay. And here we can see the simplest digital delay structure that uses a feedback type mechanism. In the comb filter video, we actually saw a feed forward type filter. We're using an FIR filter, whereas here we're using basically an IIR comb filter or feedback comb filter. And this is, in my eyes, the simplest useful delay structure. In the block diagram, we have our delay line and we have the delay line of length k. This delay line is variable, so we can vary the length k, and that would be our delay control as we saw on the TC electronic flashback. The delay control again controls the time between delays and repeats. So to feed into this delay line, we take the input on the far left side, x of n, we sum that, and then we feed that into the delay line. What we sum the input with is actually the output of the delay line multiplied by some gain g and then fed back into the summer. So therefore, the input to the delay line is x of n, so our current input sample, plus the feedback or the output of the delay line multiplied by some constant g. So therefore, there's this feedback structure which forms this IR comb filter. The feedback is also variable. This number g we can control as well. And again, this was the control on the TC electronic flashback that essentially controls the number of repeats, and these will be decaying in volume. Because now we have feedback in this structure, anytime we have feedback, we have to be cautious of stability. And in this particular case, we typically can arrive at stability if the magnitude of g is less than 1. So something like 0.5 or minus 0.5, 0.7 and so on typically is fine for stability, but we should always do our stability analysis. As a third control, we have a mix control. So we take the output of our delay line and then feed that into another gain. It's denoted by the variable m for mix. That output is then summed with 1 minus mix, another gain, times the input. So if m equals 1, we simply get at the output of this whole structure of y of n, we simply get our delay line feedback network as the output. If m equals 0, we simply feed only the input to the output. So as you can probably tell, the mix control controls between a wet and a dry signal. So if m equals 1, we only get a delayed signal, we'll call this wet, and m equals 0, we get only a dry signal, so only the input signal at the output, this is a dry signal. So hopefully you can see with a simple delay structure that already from that, we have a delay control, which was essentially the length of our delay line. We have a feedback control, which was our feedback variable g, and we have a mix control, which might be, for example, the effects level. The question is then, okay, how do we do, for example, these different sounds? So if you want a tape delay, a lo-fi, a modulated delay, ping pong, slap, and so on, well, basically we just have to do variations of that delay structure, or we choose different delay line lengths. So there are many, many different structures possible, and if you're interested in audio effects and digital signal processing in general, I'd strongly recommend checking out Digital Audio Effects, or DAFX, by Udo Zölzer, which is a great book covering many different audio effects in detail. But in his book, for example, we can see many different digital delay structures. For example, the top left is probably something very similar to what we just saw, which is this rather simple IR comb structure with the various parameters. But for example, on the bottom left picture, we might see that in the feedback mechanism with the delay line, we might add filters, which could maybe influence the sound. We could maybe get a more analog sound out of it. Or on the bottom right side, we might split our input signal into various frequency bands. So we're using a high pass filter, band pass filter, and low pass filter, and then feed those into separate delay lines, mix them differently, and we might get different structures and sounds. The top right image is an expansion of the IIR comb filter. So rather than having a single input, single output, we have a multiple input, multiple output system where we have multiple delay lines, we have a matrix feedback structure, a matrix feed forward structure, matrix blend or mix control, and this actually forms the basis of many reverbs. We can also use this to create some interesting delays. So keep that in mind. Essentially, the underlying structure is pretty much always the same. We have a delay line or number of delay lines, feedback and feed forward mechanisms. We can add in various filters, play with the variables and constants to give us different sounds and different structures. Before we move over to implementing a simple delay in C on an STM32 microcontroller and then checking out the sound results and looking at, for example, the frequency response and time domain behavior, we need to think of some practical considerations. As we alluded to before, feedback, although useful, can become a potential issue if we're not careful. So we have potential stability issues depending on the magnitude of G, which eventually controls the loop gain of our feedback. So what we could do is we could work out the difference equation, take the Z transform, and perform a stability analysis. If you're interested, please check out video number 27 on my channel, which goes over the Z transform and its practical applications, including how to do stability analysis. So you, after this video, hopefully will be able to check out the digital delay structure and its stability. One issue we have, because we are on somewhat of a memory-constrained system when we're running on a microcontroller, is the practical delay line length. If we have a mono delay or stereo delay, or if we're doing a multiple delay line structure, this becomes more and more apparent the more delay line lengths we have and the more delay lines we have in general. For example, if we take a mono 1 second delay at a sampling rate of 48 kilohertz, pretty standard for typical delays, we have 48,000 samples at 32-bit floats, which we might be using to manipulate our information in our DSP. That gives us already 190 kilobytes of RAM required. And that's just for a single channel, and that's just for a 1 second delay. No other processing going on. This is just for the delay line. Just imagine we have a 2 second delay, we have stereo channels and so on. We can easily get into a couple of megabytes of RAM required, which is far more than a typical microcontroller might have. There are, of course, possible solutions to this. For example, we might just add additional memory. That could be external SD-RAM in the case of a microcontroller, but that might give us a bottleneck on speed, because now we have external memory and we have an off-board interface, which is typically slower than onboard RAM. But it does allow us to have pretty long delay lines. Another possible solution would be simply using a lower sampling rate. So the amount of RAM required pretty much scales proportionally to the sampling rate, and we could also, of course, reduce the bit depth. So if we just go with a sampling rate of, let's say, 30 kilohertz, and we use 16-bit fixed point, for example, that would, of course, reduce our RAM requirements quite a bit. Downsampling in software before the delay is, of course, another option. So we could run our main system at 48 kilohertz, and once we enter our delay block, we will downsample in software, so decimate, and then we ease up on our memory requirements. Another practical consideration is changing of parameters in real time. For example, abruptly changing the mix, feedback, and delay line lengths may introduce audible artifacts, that could be clicking or distortion, into our audio signal, which is something we really don't want. Of course, the mix, feedback, and delay line lengths might be directly or indirectly mapped to controls that the user can change. For example, in the DC electronic flashback case, these were mapped to potentiometers. So possible solutions to that, we could smooth the control changes, so pass them, for example, through a low-pass filter, or, for example, control changes might only be allowed when the delay effect isn't currently processing. With all of this in mind, let's now move over to STM32 Cube IDE, and I'll show you how to implement a digital delay, the simple structure we saw in software, and then we'll do some tests and measurements on this as well. Now jumping over to STM32 Cube IDE, let's look at the implementation in C for the delay. I've implemented it using a .c and .h file, so a header and source file, and we'll look at the header file first. What I like to do is do static memory allocation, so I won't, for example, create variably sized arrays on the fly. Depends on how you'd like to do that, but I like static memory allocation, so therefore I do a predefine of the maximum delay line length that I can use for my digital delays in this case. So here I define this as 32,500. The reason being I'm actually running my sampling rate in my system at about 32 kilohertz, so about 32,000 samples per second. So with a maximum delay line length of about 32,000, the same as my sampling rate, I can get up to 1 second of delay. Now, of course, this is a parameter you can vary. Or you could, of course, do dynamic memory allocation. Then I like to create a structure or a struct specifically for my delay that contains, for example, the delay settings, as well as my delayed line, which is my ring buffer or my circular buffer. So in terms of settings, I have my mix control, which is a floating point variable between 0 and 1.0. That defines the mix setting, so 1 is completely wet, 0 is dry, and we can have any number in between. We also have a float, which is our feedback, and that could be any number for stability between -1 and +1, and that's variable as well. That controls, again, the number of repeats we have and how they decay. Then we have our main delay line buffer, which is our circular or ring buffer, and its structure is pretty much identical to any circular or ring buffer. We have the buffer itself, or in our case, the delay line, which I'm defining here with the maximum delay line length we defined above. Then we have the line index to keep track of where we are within that circular buffer, and then the delay line length itself. So this is actually a variable parameter and determines the length of the delay. It can go up to the maximum delay line length, of course, but it can be anything between 1 and that length. So that lets us then change the time between the repeats of our delay. And lastly, I just have a float as my current output of my delay. This struct will then be passed into various functions. First of all, we have the initialization function, which takes in the struct, the delay time in milliseconds, mix parameter, feedback parameter, as well as the sample rate in hertz. And that effectively just clears the buffers, sets up our default settings, and just makes sure our delay struct is ready. Then we have the update function, which is our main implementation, which takes the current input sample and computes the current output sample based on all of our parameters and settings and our delay line. Then we have a set length function, which takes in the delay time in milliseconds we would like, as well as the sample rate, and computes the delay line length, this parameter we saw in the struct, using our very simple equation where the delay time is the delay line length divided by sample rate, and we can rearrange that, of course, to get the delay line length, which is simply the delay time times the sample rate. Jumping over then to the source file, we have the initialization function. All I'm doing is calling my set delay line length, taking the delay time in milliseconds and the sample rate, and that will set the length of the delay line. I'm storing the delay settings, such as the mix and the feedback controls, and then I'm initializing my circular buffer. So I'm setting my pointer, my index of where we're currently at in that circular buffer to 0, and clearing the delay line, and also clearing the output. So not terribly much going on, and as you'll see, this whole implementation is very, very simple indeed, and it's not very processing intensive, which is great, other than requiring a bit of memory. Before we jump to the update function, let's just briefly look at the set length function. Here we take in the struct, the delay time in milliseconds, the sample rate in hertz. So it's very simply we can calculate the length of the delay line, taking the delay time milliseconds, converting that to seconds, so dividing by 1000, multiplying the sampling rate in hertz, and then converting that to an unsigned integer, and that's our delay line length, and we're making sure that delay line length is within bounds of our maximum array line length that we set using that to define. With that all in place, the most interesting part, of course, is then the update function. So we take our struct, and we take the current input sample, and return the current output sample. As you'll see, all this is pretty much just some feedback and manipulation of a circular buffer. So I've pulled up our block diagram on the left-hand side, a tiny bit cramped, and we have our update function on the right-hand side. Hopefully you can follow along by looking at the left and the right-hand side to see where we are within the block diagram. The first thing I'm doing is I'm getting the current delay line output. So that's at this junction after the delay line before the mix gain. So I'm getting that output from our delay line, simply tapping into the delay line at our current line index. Then I'm computing the current delay line input. So I'm starting at that node, feeding back through the gain, and then summing that with the current input, and that's our current delay line input. So I take the input, I sum that with the feedback gain, this is G, times the current delay line output. So we simply implemented this very simple feedback structure here and added to that the current input. That's the whole pretty much left side of this block diagram. Then that input, of course, has to be stored again in the delay line circular buffer. So because we've just retrieved our output of the delay line, we can store the current input at that exact same space. So we set the delay line at that index to be the delay line input. Then we have to shift our delay line index. This is our circular buffer. So we increment the delay line index by 1. We check the bounds, and if it's over the delay line length, we reset the index back to 0. This is a typical circular buffer. The only thing then we have to do is implement our mix controls, so our M and 1 minus M, to sum our output. And our output is simply the output of the delay line times M plus our input times 1 minus M. So we take our input times 1 minus M and we add to that M times the delay line output, and that's the output of this delay block. We might just want to do some protection, so limiting the output between plus and minus 1, but this should be given anyway for bounded input signals. And then we simply return the current output. So very, very simple. All we're doing is following this block diagram, and we're implementing this delay line, as we saw in previous videos, as a simple circular ring buffer. Now, again, keep in mind, this is a very, very simple structure. We could, of course, implement delay structures which are a bit more complicated. So we could, for example, have filters in the feedback paths and the feed-forward paths. We could have multiple delay lines, but all of these are based on the structure we saw here. All we would have to do for a stereo delay is have 2 delay lines, 2 feedback controls, 2 mix controls, and so on, and basically duplicate this code. If you want to do an analog delay, I might put a variable low-pass filter in the feedback path. So this serves as a great starting point to implement various different delay effects and to play around with different delay effects, but these are the pure essentials. Before we compile this code and upload this to the board, let's just check out how we're changing the parameters and how this effect is called. In terms of initialization, I'm just passing in my struct, my initial parameters, as well as the sampling frequency, and that, of course, can be changed depending on your needs. I have my processing function in main.c, which is called automatically when I get ADC streams and ADC buffers filled from the DMA. Then I loop through my samples, convert them to floating points, and then simply apply the processing. So I have an output volume control, and I multiply that by a call to my delay update function, passing in my delay struct and my current input sample. And in my main while loop, I'm checking if I'm able to change my control settings or if they're locked, because we're currently processing, and this is what we alluded to earlier, that we don't want to change our control settings while the delay is processing. I'm running through my control settings, and I'm also low pass filtering these control settings to make sure these are smooth control changes. I'm applying a deadband so they don't jitter around, and then I go through my control settings. I can control the mix of my delay, I can control the length between 50 milliseconds and 1000 milliseconds, or 1 second. I'm changing the output volume, and I'm changing the feedback between 0 and 1. And these control settings are simply mapped to potentiometers, which I have on a separate board, which are then sampled by an ADC at a fixed rate. But keep in mind, I'm making sure that the delay isn't processing. I'm filtering, I'm low-pass filtering these, and I'm applying a deadband, and then I'm mapping these potentiometers via the ADCs to various controls, so mix, delay length, output volume, and feedback. So now let's upload this code to the board and have a play around with it and see how this sounds. Here I have the DSP board plugged in with a guitar input and out going into my audio interface with ST-Link connected for programming. To vary the parameters, I've just connected up these 5 potentiometers. 4 of them are being used, as we saw, mapped to the controls. The whole device is being powered by this isolated DC brick, and we'll also be using the QuantaSilent QA403 just to briefly look at the frequency response. So I've uploaded the code to the board now, and I've added in some live expressions via the debugger. So my ST-Link is connected to the board. I can feed back expressions and look at variables in real time. So for example, here I've stored the mix, feedback, current line length, and output volume, just to give you an indication of what parameters we are currently at. I've also hooked up my QuantaSilent audio analyzer to the board, so I'm supplying an input to the board and monitoring the output, and for example, using this tool, I can then look at the frequency response. So currently, I just have true bypass enabled, the frequency response is completely flat, but if I now engage the effect, so I've just pressed one of the foot switches on the board, and you'll see it's recomputing the FFT, and this is the typical frequency response we get from the input to the output across the frequency range, so from about 20 Hz up to about 20 kHz. So the roll-off you're seeing on the far right is due to my sampling rate. I'm actually only sampling at 32 kHz, and my anti-aliasing filters are effectively cutting off at half of that, so about 16 kHz, and that's why we have that sharp cutoff on the right-hand side. But the actual frequency response is rather interesting and very reminiscent of our comb filtering structure, and we can see this particularly on the left-hand side, that we have these notches and peaks in our frequency response, which is very typical of our comb filtering. This is because due to the delay, we will get peaks and troughs due to being in and out of phase at certain frequencies. We would have to increase the FFT resolution to see other finer detail, but this kind of comb pattern actually continues all along this frequency response and of course changes depending on the parameters we use. I know the resolution isn't great here, but for example, changing the mix control quite a bit down, maybe increasing the line length, we get a different frequency response here, and we get less of this notching because we turned our mix pretty much all the way down, which means we get a straight feed through signal. The line lengths and the feedback will of course change the shape, position of these various comb notches and so on, which will change the characteristics of our delay. But now let's listen to this with the guitar plugged in and see what these parameters do to the audio signal. Okay, so here I have my guitar now plugged in, into the delay, into the guitar effects pedal, and right now it's just dry, so this is my bass sound. I'll turn it on with just the default settings, whatever it's at the moment. So if I hit the guitar once, you can hear these decaying repeats, and that's due to first of the delay line, but the decay is because of then that feedback, and also the multiple repeats are because of the feedback. So we can, for example, change the overall mix. So if I reduce the mix down, just my dry guitar. But if I add the mix in, we get more of the delay. So it's a blend of the wet and the dry signal, as we expected before. Then we can change, for example, the delay line length. So we have a fixed delay line length here. So I can increase that distance. So now this is a longer delay line, and we get longer spacings between the individual repeats. Whereas, of course, we can make that shorter again as well. So now the shorter delay line. Then, of course, we can play with the feedback control. So if I reduce the feedback, we get less repeats, but also they decay quicker. So this is a pretty low feedback amount. Maybe we get one similar volume repeat, and then it falls off pretty quickly. So if I increase the feedback amount, we get far more many repeats, and they take longer to decay. Now if I bring my feedback control closer to 1, you can hear basically the feedback, because it's so close to 1, takes very, very long to decay. And you can imagine if the feedback equals 1, we're pretty much never going to get a decay. But in this way, this is how most digital delay effects work. Of course, you can add in filters, add in different delay structures. Already with this simple structure, the delay is very, very flexible and very typical of a pure digital delay. Thank you very much for watching this video. I hope it was useful, and I hope it gave you some insight on how to develop your own digital guitar effects pedals and effects, specifically in this case, a digital delay. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware, PCB design, DSP, and embedded systems videos. Thanks again for watching, and I hope to see you in the next video. Bye-bye.